Yes, Nimai Mondal, do you have any question? Hello. If you have any question, you can switch on your audio and you can say, or else you can text in the chat box if you want.
Not audible.
Not audible. Oh, sorry, sorry. Uh, yeah, Nimai Mondal raised a hand. If you have any question, you can ask or you can put it in the chat box. So, if you guys have any question, any doubts regarding the previous week, or if there is any doubt in this week also, you can check if I have switched on the audio. Yeah, so if you guys have any question regarding the last lectures, any issues with the assignment questions or something, you can ask. So today we'll be discussing about the lecture or week two lectures and some of the assignment questions, similar assignment questions, so that it will help you in this week's assignment. Till then, if you have any questions or any doubts regarding the last week's lectures, you can ask. We'll start the session at 6:10. If someone joins, so we'll wait for some more people can join. Okay, so we'll start the session today for today's this week's lecture, that is week two's lectures. So let's jump onto the presentation directly. Okay, so I hope you guys can see the screen. Okay, so let's start today's tutorial. So today we'll be discussing about the week two lectures and some of the assignment questions that will help you doing the assignment questions for this week. Okay, let me see something joining. Yeah, yeah. So let's start anyway. We are starting. I hope you guys can see my screen. Ah, okay. So as I was mentioning that today we'll be going through the week two lectures or a summary of week two lectures, followed by some of the assignment questions, not this week, the same assignment questions, but similar assignment questions for this week that will help you uh, solve the questions that are assigned to you for this week. Before that, let me introduce myself. I am Balram Shah. I am the PMRFTA for this course, that is Watershed Hydrology. I am a PhD scholar at Interdisciplinary Center for Water Research at Indian Institute of Science, Bangalore. So in this, so before that, if you have any questions or any doubts regarding the last week's questions, you can just ask. You can unmute yourself and you can speak, or you can put it in the chat box also. So in this week, what all we have studied? Okay, I'll share some other screen. Let me go here again. Give me a minute. Yeah. So last week only we have explained what is watershed. Okay, I'll just show it again. So I'll suggest you guys to go through the uh, lectures before coming, because it will help you to uh, understand like what will be the doubt for you guys, so that you can ask directly that here. Okay. So last week we have studied that what is watershed. So let's say any area of land, any water that is coming on that land, if it drains at one outlet point, then it is called as watershed. So let's say you have a mountain, right? Now, if what rainfall is coming and it is coming on the left hand side of the or left hand side of the mountain, then what will happen? It will come only in this direction based on the slope, right? And this will join the river, and then at the end in the sharing screen, you can see that it will reach here and it will go to the one of the outlet point. So again, if you consider the same mountain and rainfall falls in the right hand side of the mountain, what will happen? It will go to other direction, right? So if you consider the whole mountain area, it will not have the same outlet point that the water is draining. So the area which is having the, if whatever amount of rainfall or whatever input precipitation is there, if it joins to a single outlet, then that is called one watershed. Okay, like that, in one watershed, in a bigger watershed, you can have smaller sub watershed also. Okay, any other questions in this? If not, we'll move to this week lectures. Uh, okay, I hope you can see the screen. I hope I answered your question. Okay. Okay, so before moving on to the questions, we'll just see a little of what we have studied in the. So in this week, what all we have studied? We have studied about what are the hydrological abstractions in the hydrological cycle, right? So what what we have studied? We have studied about the hydrological abstractions. So, what is hydrology and all? We have studied in the last class. So, the new term that we have right now is abstraction. So, the literal meaning of just the word abstraction is like taken away or pulled away, right? So, if we draw away something, then that process is called as the abstraction. So, here, what we are calling abstraction as simple laws. So, any laws that is happening in the water hydrological components, we call that as hydrological abstractions. So in this hydrological cycle, you can see that precipitation is the input, that is not the loss, right? So let's say precipitation is number 4, then evaporation is happening, number 1, whatever you can see. So evaporation is one of the laws that is taking place, right? Second is transpiration. So we'll come to all of this term one by one. Then we have runoff. So runoff is available to us. So we'll not consider that as abstraction, right? Then we have depression storage. Depression storage also will come later. So these are then interception, infiltration. All these are hydrological abstractions that is happening in one watershed. Okay. So firstly, let's understand that why why we need this abstraction, or like why we should study about this abstraction. Anyway, we have discussed that what is abstraction. Abstraction is the process by which water is removed from the natural hydrological cycle or the watershed. Either it can be because of human activities, or it can occur naturally, or because of some infrastructure that we are developing, something like that. So it can have any cause, but any laws that we are facing in the watershed, that will be considered as the abstraction. Now the question is, why should we study about all these abstraction like evaporation, transpiration, interception, infiltration, depression, storage, and all that? So, firstly, if we understand all these abstractions, it will help us, or like all this abstraction will impact the availability and the distribution of water or water resources in that region, right? And it will also help us determine the other hydrological components that we need. The most important component that we need is runoff, right? So that also we can get if we know all of these hydrological abstractions and so on. Okay, so first one was, as I say, let's say interception. Interception is one of the hydrological abstraction. So interception happens when water is going away from the water is going away from the vegetation above the ground. So whatever vegetation, it can be crop, it can be tree, it can be forest, any water that is taken away from the vegetation from the ground, it is considered as the interception. Okay. Next, we have depletion storage. So, what is okay, and depletion storage is kind of superficial depressions or hollows in which water gets stored. So, we'll study all this one by one. Then, what is evaporation? Evaporation is like any water that is removed from the land, or I mean soil or water, that is, or open water, that is considered as evaporation. Now, second is transpiration. Okay, so what is transpiration? Transpiration is like whatever water that is taken away from the leaves or like that, we'll consider that as transpiration. Okay, we'll study all this one by one. Then we have infiltration. Infiltration also is one of the important hydrological abstraction, or that we will study in this lecture. Okay, okay. Uh, so let's start from the interception. As I mentioned, what is interception? So interception is defined as the precipitation, or whatever precipitation water has been occurred, the retained water on the drainage basin through its if it is let's say some objects, let us say leaves or other vegetations. Okay, so it can happen on whatever water is stored or is there on the leaves or other vegetations or vegetation, then maybe buildings. Anyway, other than that, let's say if it is happening from animals also, all this will be defined as the interception. Okay, so interception. Okay, so we'll move to interception directly now. Okay, so first hydrological abstraction is interception, right? So this interception, as I mentioned, interception, I have explained what is interception. Now this interception, let's say if I write it as I, this is a function of, so this interception will depend on what all. As I mentioned, what is interception? It will be the water that is retained or taken away, retained and then taken away from to the atmosphere on the leaves or vegetation or animals or buildings, anything, that is called an interception. So mostly this interception happens, the dominating area is the vegetation part. Okay, so it is a function of vegetation type, because different, if let's say if different vegetation type is there, so let's say if you have deciduous tree and you have coniferous tree, the amount of water that will be stored firstly on the leaves of both of these tree will be different, and hence the evaporation or the interception that is happening from this vegetation type will be different, right? So interception will be a function of vegetation type, then it will be function of the age of that vegetation, right, and so on. Now these vegetation type and age we calculate through leaf area index. So leaf area index, if I say roughly, leaf area index is defined as leaf area to the soil area. So let's say one tree is there. Okay. So let's say this is the tree. Now let's say on one leaf, the total area of one leaf, and this vegetation, let's say it will cover this much of region. Okay, this much of region. So the ratio between the leaf area and the soil area will be called as leaf area index. So the main basic for this leaf area index is the same. There can be some different ratios like that. I mean, the main basic thing is this only. So it will depend on the leaf area index, and from this we can calculate the interception also. So this is one dimensionless number, right? Dimensionless number. Okay, so it can be a function of other things also. Let's say it can be also function of precipitation, then intensity of the precipitation. Precipitation as in all the factors: intensity, frequency, then also duration maybe, and then type of the precipitation that is happening, and so on. Okay, so the in this diagram you can see what is the main, as I said, dominant part is the vegetation. So we'll see that. So this infiltration will be because of the canopy loss, or we can say crown loss, plus it can have through fall. So what is this canopy loss, or let's say crown interception loss? The canopy loss, or let's say if we say EC, is the amount of water which is intercepted by the crowns. Crowns as in, let's say if tree is there, the upper part is called as crown. So if the amount of water that is intercepted by the crown of the vegetation, that is called as canopy loss. Okay. Then through fall, then whatever water that is now some water will get evaporated from the leaves and some water will fall from the leaves. That fall that is happening is called as through fall. Okay, or through fall. Then we have interception from the forest floor or any litter. So as let's say if you are in the forest, what will happen? All the leaves will be shedded and the whole area will be covered with, let's say, leaves, stems and all. So the water that will come, it will not go directly on the land, but it will be on the leaves, surface and all. So whatever interception is happening from this area or this forest floor or littering is called as forest floor interception loss. We'll write it as, let's say, EL. Okay, and next we'll have stem flow also. So as I said that whatever fall is happening from the leaves, that is called as through fall. And if some water will be dripping from the stems and branches and all, right? So that is called as stem flow. So these through fall, stem fall will be very minimal. Okay, but the main part of the interception will be canopy loss and forest floor loss, forest floor interception loss. So this interception loss from the canopy can be, we can get this EC as Rg minus Rt minus Rs, where Rg is what? This is the gross precipitation. Okay, so I'll write that. This is the gross precipitation. What is Rt? Rt is the through fall, let's say. So if you know everything and like through fall, forest floor and all, so let's say this is the stem flow and we are considering that there is no forest floor. Let's see, we are writing EL. See this EL also, that is forest floor, later also we can get the value using some experiment. So this all things has been discussed in the lecture. So what we do, we put one we take one sample and then we cover the stems and then we see how much is interception is happening from that, and then we see that after let's say we'll collect that sample and then we will weigh that sample of the forest floor and then we'll see how much interception has happened. Okay, and then from there we can get the EL or the forest floor liter, whatever interception has happened. And remaining is from the gross precipitation through fall and stem flow, will get the canopy loss. So this gross precipitation, how we get? We put rain gauge nearby the openings. So let's say if vegetation is here, we'll wherever openings it is there, we'll put one rain gauge there. We'll take the precipitation from there. That is called as gross precipitation. Next, this through fall. This through fall will get from the rain gauge itself, but it will be under the canopy. So let's say if in the figure, if you see, so let's say we'll put one rain gauge here and whatever value we are getting from here, we'll deduct from the opening and then we can get this through flow. And then stem flow, what we do from the main stem or the main stem of the tree, we'll put a collar there. Okay, and whatever value we are measuring from that collar, we can get the stem flow. Okay, so generally the interception will be around 3 to 5% of the precipitation. Okay, so this is one way by mass balance, let's say. Next, we can have like how other way, what are the other ways that we can measure interception? Firstly, we have Jensen model. Sorry, I mean models we have. These are empirical model. Jensen model we have studied all this. So I'm not going into detail for this. The Jensen model is for agricultural crops. Then we also have Horton model in 1991 or 1919 something. It's some here. Okay, so Horton model was used when there will be precipitation event. Also, canopy storage is there. Okay, so all these models we can use to get the estimate of interception. Okay, I hope the interception is clear, right? So this is how others. There are others also like Merriam model is there. Merriam model is there, which was in 1960s. So this Merriam model is a modification of the Horton model itself. Just that in this we consider one exponential decaying term. As the precipitation increases, we are saying that we are having one exponential decay term. Okay, and that is how we get to the interception. Next abstraction was depression storage, right? So what we studied, what is the depression storage meaning? So depression storage we also called as ponding. So from the word itself you can understand that there is some depression and in which something is getting stored, right? So depression storage or ponding is any water on a drainage basin that drains into closed depressions, right? And also these directly never reaches to the outlet of the basin. If let's say there are huge amount of water in a depression storage, then it can flow through as a base flow or the groundwater flow, or it can get evaporated at the end. Okay, so this is the depression storage, and this in this what is happening? The water is remain trapped in the depression, and as I said, some will be evaporated and some will go as a groundwater flow or base flow. So let's say so this depression. Again, it can be measured using hydrological, or it can be estimated using the hydrological budget equation, water budget equation. Like, let's say if you are writing depression storage as DS, then it can be written as rainfall minus runoff minus infiltration minus evaporation minus interception and all that. So simply, if you use the water budget equation, you can get to the depression storage, right? This rainfall we have seen how to measure using rain gauge or any other estimates we can do. Evaporation also we'll see that evaporation can also be measured. The runoff also can be measured. And this infiltration and interception, this is estimated using some model or something. So in interception just now we have seen that how we can measure or estimate, and infiltration also we'll see at the end. Okay. Other than that, this is simple hydrological budget equation or water budget equation. Okay. So other than that, we can again have some models or some empirical equations. So models of superficial depression. Okay. So it was given by Lindsley et al. In 1949. There was one equation given by him, by them, and then we can estimate that what is the amount of water that is stored at any time t. We can get from the equation given by Lindsley et al. 1949. Okay, so the equation was like V equals to St into 1 minus e to the power minus k into P. right? So here V is the volume of water that is stored in that depression at some time t. Okay, and the what is SD? SD is the maximum depression storage capacity. So any depression, if we have, it can have only a maximum capacity that it can hold, right? So that maximum capacity is called as um, SD. Okay, and PE is the excess precipitation that we have, and this constant K can be written as 1 by SD. And like that, you can estimate that what is the depression storage value, or how much storage that can be possible or is there at time t. Now, from this equation, if I say that the not the effective precipitation, the precipitation excess is very large. We have a very large value of precipitation excess. Can you tell me that how much will be the um, V, or let's say the amount of water that will be stored at a time t? From this equation, you can understand if you have a large value of excess precipitation or PE, then what will be the value of V, or like where it will approach? Anyone? So these tutorial sessions are, so I'll suggest, like, if you're joining this, it is good for you. Why? Because in this tutorial session you can interact with us, right? And so that any doubts that you have, you can uh, get solved. Also, if you don't interact, if the doubt will only not arise and you will not get it solved. So better if you can interact, anyone can answer. So what I was asking is, if there is a very large precipitation excess, okay, this means Pe is very high. This means what? E to the power minus, let's say, infinity. So what will be the value for that? It will be 0. So it will be very near to SD, right? And what I mentioned, what is SD? SD is the maximum depression storage capacity. So physically also, if you think, like, lot of precipitation excess is there, that means what? The whole depression storage will fill, right? So if precipitation excess is very large, then the volume of the depression storage will be at its peak, so it will be equal to SD. And when there is a very low precipitation excess, then what will happen? Then V is also very negligible. So if, let's say, very no precipitation is excess is there, there will be no capacity or no water that is getting stored in the depression, right? Okay, so next we'll move to some questions, then we'll come back again. Okay, so the first question that we have is, which of the following surfaces will have the most pronounced interception? Can anyone tell? So as I mentioned, that interception will be from each of the, wherever water can be retained, the interception is happening from there. But the question is, yes, yes,
Option C.
option C, dense forest canopy. Correct. So the most part of the interception that is happening is from vegetation. So the correct answer will be dense forest canopy. Right. Okay. So the next question is, the factors having directly proportional, that is evaporation increases with an increasing factor. Okay, so we have not discussed about evaporation. First we'll discuss evaporation. I don't think we have questions on depression storage. Oh, sorry. So first, now we'll move to evaporation. Okay, so the next abstraction is evaporation. So as I mentioned, what is evaporation? Evaporation is the process where liquid water is converted into gaseous water, right? So there is a change in the phase of water. That process whereby liquid water is converted to water vapor, right? And mostly the evaporation that we'll call as evaporation will be from the land surface and open water surface. Okay, so any evaporation or any process where liquid water is converted to water vapor and happening from land or open water surface, we'll call that as evaporation. Okay, so in this, what is happening? This is happening because by the transfer of water molecules to the atmosphere. Right? Now again, there is okay. One thing is, so there can be different models which we work. So it can be event-based modeling models, or it can be continuous models. So what I mean by, sorry, shit. Okay. Okay. So what I mean by event model and continuous model is, event based model means that is one event based. So in the last week lectures we have seen that what is an event. Let's say a rainfall event. Rainfall event means a event when rainfall is happening. So let's say when rainfall is happening, in that situation what happens when much amount of rainfall is happening, in that case evaporation is very less compared to when when precipitation is not happening. So let's say when precipitation is happening for 1 hour, let's say, okay. So in that 1 hour or in that event, if only if you see, then in that case, what will happen? The evaporation will be less. But if you consider 1 month and you want to, you're knowing that how much precipitation has happened in this 1 month, right? So this is a continuous model. So in this evaporation is will be much. Okay. So in event based modeling, we can neglect the evaporation, but in continuous model we can't neglect the evaporation. Okay, I hope this event based model and continuous model is clear. Okay, so now coming to factors that affect the evaporation. Okay, so this is very important because we should know that if we are understanding one any process, so we should know which all factors can influence that component. Okay, so that whenever we are modeling that, so let's say we want to estimate the value of evaporation, but with all the physics involved. So in that case, we should know that which all factors are influencing my component, so that if I want to make a model which will estimate the evaporation, then in that case, if we know that okay, these factors influence the component in this way, so in that case we can physically model the component, any component that we are going to estimate. So for that we need to understand that which all factors are affecting the evaporation rate. So firstly we have vapor pressure. Vapor pressure at both the water surface and also the vapor pressure and the air that is prevailing above. Okay, so the vapor pressure will. So what is vapor pressure? Vapor pressure, we know that vapor pressure is the pressure that is exerted by a vapor when it is in its condensed phase, that is solid or liquid phase. At a given temperature, the pressure is exerting. So that is called as vapor pressure. So we know that. Okay, so we can. So Dalton's law of evapotranspiration gives EL, wherever I am writing EL from now onwards, it will be considered as the evaporation loss or evaporation rate. Okay, so EL is equals to C into EW minus EA, where this E, you can see E is the vapor pressure. EW means the saturation vapor pressure, at water temperature, and EA is the actual vapor pressure in the air. Okay, so this is given by Dalton. So Dalton's law of evaporation says that rate of evaporation, so whatever evaporation rate is happening, is directly proportional to the difference between the saturated vapor pressure and the actual vapor pressure in the air. Right. Okay. So next factor that affects the evaporation rate is wind speed. So we know that if the wind velocity or wind speed is more, then what will happen? Whether the evaporation loss or evaporation rate will be higher or lower, anyone tell? So what this winds does, wind will help you, like the evaporation, what is there. So let's say wind is blowing, okay, and evaporation is taking place. So in that case, when wind is blowing, the wind speed will take the water vapor from the zone of evaporation, and hence the rate of evaporation will increase with the increase in wind velocity. So let's say if wind velocity is increasing, the rate of evaporation will also increase, but up to some limit. So that limit is called critical wind speed. So I'll write it here. So if wind speed is more or wind velocity is more, then what will happen? The evaporation loss, or I'll write it as here will be more, but up to a certain limit, right? That is still critical wind speed. After that, critical wind speed. After that, it will have saturation. Okay. Next factor is air and water temperatures. So we know if the temperature is more, evaporation will be more. Evaporation will be more. Okay. So rate of evaporation, we know if the temperature will be more, then the evaporation will be more from both the air and water. Okay. Next factor will be size of the water body. Water. Okay. So let's say you are considering a big reservoir and a small pond. So in that case, if the size of the water body, so let's say if lake is there and a big reservoir is there. So in the big reservoir, obviously there will be more transport, more evaporation. Why? Because so this large water bodies will have high evaporation because it has high wind speed. Okay, and also the area is more. So in that case, evaporation from that large water bodies will be more. Okay, then we have atmospheric pressure. So as the pressure decreases, or in the high altitude region, we know that atmospheric pressure is low, because so we have studied that, so we are not going to that. So as we move up, the atmospheric pressure will come down and it will increase the evaporation. Next, we have soluble salts. So we know that if there is any impurities in the water, that will hamper the evaporation, and hence the, so let's say if soluble salts are there, or maybe some any of the impurities are there, it will reduce the evaporation, right? So we know why we put salt in the boiling water and all. We are not going deep into all those because we know this. So we know that evaporation from saline water bodies, so evaporation loss from saline water bodies, let's say sea or ocean, will be 2 to 3% less than that of fresh water, right? Okay, next factor is, okay, so that's it. Okay, so these are the factors that affects the evaporation. So other factors are also there which affects the evaporation, but the main factors that dominantly affect the evaporation are these. Okay, next, now we know that so we are, what we are doing, we are knowing all the components, or what are the hydrological abstraction, what is the process that is happening. Then we are knowing that what all factors affects those component. Then we also should know that how we can measure those, so that we can incorporate in that in our model, or we can estimate the value of it, right? So uh, how we measurement of evaporation. So mostly evaporation we measure using evaporimeters, right? So okay, I'll show that first. So we measure the evaporation using evapotranspiration, right? Okay. So this one, can anyone tell that what is this? What is the name of this? Anyone?
It's a pan evaporator.
Yeah, pan evaporimeter. But so we have different kind of pan evaporimeters. based on some of the improvements, we'll see that. So this is called class A pan evaporimeter or evaporation pan. Okay, so this one was very old kind of, very, I mean, now also it is used at many places, but it is one of the oldest evaporimeter that has been in the use. Okay, so in this, the sheet you can see is of galvanized iron. This is GI sheets, okay, which is unpainted. Okay, and we can see on below the unpainted this evaporative meter we have one wooden platform, okay, above the ground level, and it is around 150 millimeter above the ground level. So why we are keeping this wooden offset, this we are keeping so that air circulation, free air circulation can happen from the ground. Okay, and how do we measure the evaporation depth? At the end, cylindrical thing you can see here, this one. So here we have one measuring device. So a hook gauge will be there which will measure the evaporation depth. Okay, so as we have learned in the last class also, that at 8:30 in India, at 8:30 we go and measure the precipitation from the rain gauge. Like that, at similar time we measure this also, and then what we do, whatever evaporation has happened, we'll see that, and then again we'll get so daily evaporation we can measure from this. So in this, can you tell me what is the issue, that is like what improvement we can do to this pan or to this evaporimeter? Anyone? So as I mentioned that this GI sheets, you see it is unpainted. So now if it is unpainted, or what is happening because of this sheet, the evaporation is taking place from all the direction also, right? So then comes this. What is this? This is the ISI standard pan, which is mostly used in India. Okay, this is ISI standard pan, right? So this is also a modified version of class A pan evaporating meter only. Just the change that you can see from in this both the figure is what? One simple change that you can see is that top of the pan is covered. So in India, what happens that every time we are not checking around this evaporimeters or any of the instruments that we have. So whatever water is stored in there, birds and animals will come and then they will drink and all. So if we don't keep an eye on that, that will also be considered as evaporation, right? So for that we uh, covered that with a hexagonal wire net of GI sheets. So we have a top covering which is protecting the water in the pan from birds or animals. Second, which is the most important, it is 1.9 mm. This is 0.9 mm thick copper sheet tinned inside, and it is painted white. And why we are painting this white? So that the effect of environment heat whatever is there, it can get minimized. Okay, so the dimensions that you can see are the same for both the class A pan evaporimeter and the ISI standard pan. But again, with this improvement we are getting an improved result of the evaporation. But again we have some thing that we are missing in this evaporimeter, that is ISI standard pan. What is that? And also, as we have done all these new improvements, what we are seeing that uh, around 14%, not right here. Okay. So around 14%. So if it is uncovered pan, that is class A pan, then and if it is covered pan, then it is having 14% less evaporation that is happening from the same dimensions. Okay, so that is the change that we can see from class A pan evaporimeter to ISI standard pan. So the next question was like what is the improvement that you can make in this ISI standard pan now? Anyone? Okay, so what we can see that whatever evaporation we are seeing will be from maybe lake or maybe big water bodies like reservoirs or something like that, right? So in that case it is not uh, floating in the air, right? So it will be in the ground. So the environmental condition that we have is not the same. Okay, so next what we do is we make one pan evaporimeter which is buried into the ground or sunk into the ground, and there comes the Colorado sunken pan. Sunken pan is as in buried pan. Okay, so this is the Colorado sunken pan. So it is buried in the ground, and what is the advantage? Advantage is that both the aerodynamic and the radiation characteristics are similar to that of the lake. So in the lake, what will happen? There will be aerodynamic characteristics will be there, radiation characteristic will be there. If you want to go into the detail of that, you can refer to the Venti Chow book of engineering hydrology. In there it is like with the full derivation it is shown that what is this aerodynamic characteristic, what is radiation characteristics and all. Okay, so both of this will be very similar to lake, and hence the evaporation value that we are getting from this will be much better than compared to, or more accurate compared to these. Okay, and again where to use which evaporatometer will be depending on the location and so on other factors. Okay, and here in the end also you can see a stilling well is there. This stilling well will measure the level. Okay, other than that we have USGS, floating pan and so on. Okay, so these are evaporimeters. I hope the measurement is clear now how we are using. But again, so we have all this now, right? So in this you can see what is the diameter. Diameter is around 1210 millimeter, that is 1.21 meter. But our water bodies are very large, right? So we have large water bodies. So means what I was saying is, okay, I'll go to another. Oh, okay. So we have studied what is evaporimeter. Now, what are the changes that we can see from the real world scenario to this instrument? Firstly, firstly that it is a small model. The evaporimeters are small models, or the size of is not matching with the real world scenario, the large water bodies and all. Then we have also seen that there is some height that we are leaving in the top part or the top rim part. Okay, so that will also give or hamper the evaporation value, right? Then the heat characteristics of the pan material, because the pan material is not very similar to what is there in the water bodies. We don't have any steel structures or GI sheets in the water bodies, right? So the heat characteristic will be different. So for all this, for identical climatic and exposure condition, for each of the pan evaporimeters, we'll consider some coefficient which we can multiply with that to get to the um, so whatever, so let's say what large water bodies or lakes we have, we want to know the evaporation from that, right? So what we'll do is just multiply the pan coefficient based on what pan instrument we are using. Based on that, we'll just multiply the pan coefficient and then we'll get to the evaporation that is happening from the lake. And here and there comes the pan coefficient, or we write it as Cp. Okay, so what we do, how we are getting the evaporation from the lake. So the lake evaporation, therefore, the lake evaporation will be equal to pan coefficient into the pan evaporation. Okay, I hope why we have this many evaporimeters, we have known that, and why we need this pan coefficient into the equation and all is clear. Right? So for all these pan evaporimeters like class A pan, we have a range of zero point 0.6 to 0.8. Then for ISI standard pan, we have 0.65 to 1.10. So mostly it ranges from 0.6 to 0.8, something like that. Okay. 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 Let me see if we have any questions from here, or else we'll go to some questions. Okay. So the next question is the factors having a directly proportional or evaporation directly proportional, meaning evaporation increases with an increase in that factor relation with evaporation. So which all factors or which factors you see here are directly proportional with the evaporation? Can you tell me? Anyone?
So it is option D.
Wind speed. Okay. Anything else you see there?
Option D, air and water temperature.
Yeah, correct. So both the wind speed and air and water temperature will be directly proportional to the evaporation. So if wind speed is increasing, as I mentioned, if wind speed is increasing, then our evaporation will increase, right? Other than that, if temperatures are increasing also, it will be directly proportional to the evaporation. But atmospheric pressure, we have seen, if atmospheric pressure is increasing, there will be a decrease in temperature and so, evaporation. So the correct answer will be C and D. Okay, so the next question is in combined method of evaporation estimation, combined method as in both the aerodynamic and radiation method, the contribution of wind velocity gradient and the specific humidity gradient is dash percent of heat energy. Okay, so we have not gone to the derivation. I'll just mention the value. So both the wind velocity gradient and specific humidity gradient will be 30% of the heat energy. Okay. So we'll move to the next question. That how does the humidity will affect the evaporation? Can anyone tell? I just discussed all this. See, humidity as in if the air becomes more humid, then how it will affect the evaporation? If the humidity is more, then what will happen? The air molecules will be more saturated, and hence the evaporation will be less. So, what will be the answer?
Option D.
Oh, okay. It's not like directly related. So, if we are okay, okay. So B also is correct. Lower humidity will increase the evaporation. Okay, that means okay, okay. So that is a kind of mix of the. So correct answer will be B. D also you can say. So next is which surface type generally has a higher evaporation rate? Yeah, this is easy. Okay. Yeah. So see, if you see properly in forested areas, we have not moved to transpiration yet. So mostly it will be because of the transpiration. Evaporation will be there. But in this, all these options that we have given, that is forested area, concrete surface, wetland, and snow-covered surface, will the most evaporation that will happen will be from the concrete surface. Okay. Okay. The next question that we have is the chemical that is found to be most suitable as a water in evaporation inhibitor. Water evaporation.
So,
Sorry.
sorry for the interruption.
Mhm.
So from the concrete surface, can it be the more evaporation than the wetlands?
Yes, because see in wetlands, what will happen? We have plants also. I mean, vegetations also, right? So most of the part will be because of the transpiration. Okay, evaporation will also be there, but let's say in the same area we have. So we have let's say 100 kilometer square area wetland and 100 kilometer square area concrete surface. Now, if you put water on the concrete surface and if you put wetland on the like for the same 100 kilometers square, what do you think? Which one will evaporate faster?
But most of the cases on the concrete surface, everything will move and run off.
Right. So we are not saying like runoff is there. So let's say here we are saying just the surface is having water, stored water. Okay, runoff we are
But
not
when
considering
compared
here.
to
So
when compared
if
to wetland and concrete surfaces,
Mhm.
so most of the cases the concrete surface water will move on to run off, and
Yes,
on the wetlands it will be stored on the surface, and the evaporation gets on the more higher rate.
correct. So what I meant was, if let's say the water is stored at both the same area. So let's say 100 kilometer square area wetland is there, 100 kilometer square area concrete surface is there, and the water is stored there. We are not considering runoff. Obviously, in real world scenario, if you go, mostly if slope is there, the water will flow. Now let's say the slope is not there and water has been ponded there. In that case, what do you think what will happen? In that case, I'm asking. So if say runoff is there, obviously water will flow as a runoff and less evaporation will be there. That is correct.
In that case, it is okay, but depends on
Yes.
the temperature.
Yes, true.
Yes.
So what I'm saying is same other conditions, the same area, same everything. In that case, what will happen? So in that case, concrete surface will be the answer for this question. Okay. Okay. So let's move on to the next question. The question is the chemical that is found to be most suitable as a water evaporation inhibitor. So water inhibitor as in which will reduce the evaporation. Can you tell me? So this is not mentioned in the lecture, I guess. Okay, just to note that any chemical that you know is mostly used uh, or most suitable for water evaporation inhibitor is what? Anyone? So we generally use cetyl alcohol for that. So the correct answer will be cetyl alcohol. Okay. Okay. So next question is pan factor. Pan factor as in this pan factor. It is my pencil. Pan with pan factor I meant pan coefficient. So pan factor used in the pan evaporation method is dependent on any answer? Anyone? So pan factor or pan coefficient will be dependent on both the season as well as the location. Right?
Location.
Yeah. So the correct answer will be C. Okay. Yeah, so we can do this. So the question is, a canal is 80 kilometer long and has an average surface width of 15 meter. Okay, if the evaporation measured in class A pan is half centimeter per day, the volume of water evaporated in a month of 30 days is how much in meter cube? Can you guys just do, I'll give maybe 2 3 minutes. If you guys have note or pencil, can do. I'll suggest if you don't have to now or today, please be there with the notebooks and pens so that you can do along with me. Okay, if no one is carrying, I'll do, or if someone is doing, then I'll stop for 2 minutes. I'll stop for 2 minutes. Let me see if someone is doing. Just mention what is there. So we have pan evaporation as it is class A pan. Okay, I'll mention that for class A pan, the average pan coefficient is 0.7. Okay, pan coefficient for class A pan is 0.7. And evaporation is half centimeter per day. Uh, Total time is 30 days. So you need to find out how much. Okay, I'll do then. So total evaporation that is happening from pan is how much for the whole month, that is 30 days. Evaporation will be 0.5 centimeters. So let me convert into meter. 100 into total 30 days. So how much we are getting? Sorry. 0.15 millimeter, right? Sorry, meter. I'm changing it into meter. Right? So the total evaporation that will happen from lake or canal, canal evaporation will be equal to pan coefficient into total pan evaporation, right? And total volume that we need, sorry, volume of water evaporated will be equal to the total evaporation that has happened into that area, right? So 0.7 into 0.15, 80 kilometer, that is 80 to 10 per 3 meter into 15 meter. How much we are getting? Just 2.7 to 10 per 3 to 15. So I'm getting something like this meter cube. I hope you guys are getting the same answer. Yeah, so correct answer will be D. Anyone has any doubt here? Okay, if not, we'll move to the next question. Okay, we'll move to the next question then. Evaporation pan corresponding to
So it is 12,600 only.
12,600. No, no, 1,26,000, something like that. That is what I am getting. There will be some. You can just check once. Okay, can I move then?
No, it would be.
Where you are getting? I did calculator only. I didn't do anything myself here.
So the total volume is around 1,20,000 only.
1,26,000.
1 lakh. No, you're saying that the evaporation loss is more than the total volume.
No, I'm saying the total volume of the water that has been evaporated is 1,26,000 meter cube.
Oh, okay.
Hmm.
Yeah, okay. It is on 12,000. Okay, it's right.
Okay. So we'll move to the next question. Next question is evaporation pan corresponding to Indian standard, that is ISI pan. Okay, is installed at the bank of the reservoir. The water surface area on a particular day is 100 hectares, and the recorded evaporation loss. Okay, uh, the recorded evaporation loss from the pan is nearly 4 centimeter. Okay, the anticipated evaporation loss from the reservoir for that day is dash cubic meters per day. Per day, as in for that day only. So if you need the average value for ISI standard coefficient, it is 0.8. Okay, just try once. Okay,
So
so
is it
I'll do
40,000 till
40,000. Let me check. I'll do. Okay, so as I mentioned that pan coefficient is zero point 0.8, right? So depth of evaporation will be how much? It will be zero point 0.8 into how much we are having in the pan is 4 centimeter, right? So 4 by 100 is much meter.
so this 32,000.
Might be 0.8 into 4. It will be 0.032 meter, right? So total volume of evaporation will be this depth of evaporation, that is 0.032 meter into the water surface area. What is the area? Area is 100 hectares. 100 hectares as in 10 to the 4 meter square, right? So 1 hectare we know it is 10 to the 4 meter square. Okay, just multiply this into 10 power 6. Yeah, so it's coming as 32,000 meter cube, cubic meter per day, as in for that day. So correct answer will be B. I hope you guys are getting the same, right?
Yeah, yes.
Okay. So we'll move to the next question. Okay, for this we need evapotranspiration. Okay, fine. We'll move on to the next part. What we have discussed. Okay, till here. Okay. So what up to what we have uh, done was till the measurement of the evaporation. Now this evaporation can also be estimated using. So I'll write here. So for, let's say, from any water surfaces, we can determine this evaporation using water budget equation. Very simple. That is, let's say, EL equals to precipitation minus runoff minus change in storage. So let's say if some groundwater discharge is happening, that we can minus and we can get to the water budget equation. Second is the energy budget equation. So from there also, so let's say from the if we consider the net radiation as the evaporation loss, then you will get that how much is the total radiation minus total radiation minus the groundwater ground heat flux, whatever is there. So all that you can just subtract and get to the evaporation rate or evaporation loss. Sorry. Okay. Next we have empirical formulas. So there are several researchers or scientists who have worked on several data, or maybe from the several data from the several location, and they have come to some of the formulation, or we see it as, so there are several empirical formula from which you can get the estimate of the evaporation. Okay, so till now, so evaporation is a very thing that we can directly measure properly. We have seen that what all pan evaporimeter have problems. Now also we can see there are several uh, improvements can be there in the pan evaporimeter, and hence because of that, researchers have also thought that how we can easily get without those measurement or something like that. Okay, and that's why with all this data, what they have done, they have got to this empirical formulas. So several empirical formulas are there, such as Mayer's formula is there, then some more formulas are there. So we have Mayer's formula. So mostly in the exercise and all, they'll give Mayer's formula only, where evaporation loss, or EL, is equals to Km into EW minus EA, as we have seen in the Dalton's law of atmosphere. EW minus EA into 1 plus Q9 by 16. Okay, so we know EW is the saturation vapor pressure above the for at the given water temperature. EA is the actual vapor pressure in the air. U9 is the wind velocity at 9 meter from the ground surface. Okay, and this EL is, as I mentioned, the EL is the lake evaporation in millimeter per day. Okay, and U9, as I said, is the